improve its capabilities? No, it's done. It's done. I talked to GE about that, and the engineer said it will not. Will the LEDs improve their efficiency? You bet. So hang on to the LEDs. That's where we're going. And the sodium vapor's going away. There's Phil Sadler, the proud papa, just before we took it apart and shipped it. The hydroponic system slides in and out. And I want to show you Lane demonstrating the three-part nutrient film technique tray. You see it's only about 1 meter long, about 3 feet, but it has a false bottom in it. The reason being, we want to have these little trays that we could actually, once they took the plants out, they would fit in the dishwasher again. So they could actually clean them in the dishwasher. But more importantly, why it has the false bottom is because the water, we want to have inflow and outflow from the same side. You can think about why you want that, but that's logistics. Talk about that. But in essence, to do that, you need a false bottom, and also to prevent the roots of the lettuce from going back to the discharge and blocking it up. And that's basically, there's the insert, false bottom, and we could then not have blockages. We could not expect that a volunteer would always want to check every one of those rows to make sure it didn't block up. Because when it did, it flooded. Of course, we put a drain in the floor so that we could solve that problem too pretty easily, but it just doesn't look good when flooded. Particularly when it's a National Science Foundation project and this is their special baby. It's interesting the people who came down here to see that we pay their salaries from the Senate. So anyway, we won't go there. There we are. Later on, harvesting about 65 to 100 pounds per week. And 240 square feet. Somehow it got 10 square feet smaller. I'm not sure how that happened. Yeah, the idea being that this is equivalent to about 50 kilograms per square meter per year of production. And we just talked in one of the sessions about somewhere between 75 as kilos per square meter per year for tomatoes in a high efficiency greenhouse growing one crop at an optimum environment. Here we're doing polyculture, less than optimal environment, and getting about 50 kilos per square meter per year. That's total production. What it does, it gives you some idea of a benchmark of are you producing what the plant could possibly do if it was in the sunlight. This is what the front room was used for, other than there was a telephone there was a computer there, but they had special nights where you could have your date night. And you better make sure you stay friendly with the other 59 people you're living with. Don't make a lot of enemies over that long 8-month winter. But this is a married couple celebrating their anniversary. And the bottle of wine, I'm not sure. We didn't grow the grape. I'm not sure where that came from, but they fed them very well. Oops. Okay. Again, just some names of people who helped with the project to make it functional. Faculty of the Controlled Environment Ag Center, students, as well as staff. All right, that was then an example, and the 10 to 13 grams came from that system. Let's look at bioregenerative life support system. This was a NASA project, and it still is a NASA project to be able to produce food, oxygen, and fresh water from a plant-based system in a closed hydroponic system. There's the details if you want to read it once it's online. There's a lunar greenhouse. 5.5 meters long is about 18 feet. 2.1 meters is about 8 foot in diameter. And it was theorized that this could provide half of all food calories for one astronaut, all of the water needs for the astronaut on a daily basis, and all of the oxygen needs. And that's what we were trying to demonstrate. So using the plants for true life support and really packing them in. This happens to be a crop of tomatoes from an older study. We've been doing this for many years before NASA gave us any money to develop it. You can't just create this overnight when you get a project. So after the South Pole in 2004, Phil started working on this concept, and we supported it at the center. There we are at about 2/3 full. And I usually have a picture on transplant day, and this about 45 days later, which is tremendous. But that's what we're monitoring. How much energy goes in, how much water do we use, how much nutrients have to be in that water, how much carbon dioxide we need to provide to the plant, because whenever you're using lighting in a closed system that you're not venting to the outdoors, meaning to bring in fresh carbon dioxide, you better have a carbon dioxide source. You have to, or else you begin wasting the value of those expensive lights to operate. And then labor, we looked at labor. And our output, yes, oxygen, water, and biomass. Was the idea. This is the concept of taking the robot to go to the moon in advance, to go to Mars, and set itself up. There's a whole, you can Google online, lunar greenhouse. There's not many of them out there, so you'll be able to find a number of YouTube videos about how this would work. But if you look at it from a top view, you see the 18-foot long growth chambers, the food growth chamber, the lunar greenhouses on each one of those legs, and in between is the work areas of the station, basically. So part of your space has to be taken up with the growing system, but that's how Bill envisioned it. And there we are, taking more pictures. Let's look at some numbers from that, so you know how I got that 13 grams. Biomass increase on a daily basis, 60 grams, that's what that says, 60 grams per square meter per day under those lighting conditions, which was a 16-hour day at about 400 micromoles per square meter per second lighting intensity. 400 micromoles is about 20% of full sun at noon here in Las Vegas, in the sun. 20%. The sun's over 2,000. So 4 times 5 is 20. There it is. So that's the lighting conditions. Water consumption, 25 liters per day, but we got back 21 liters. We just lost some. It's not a perfect system. We say it's closed, but we also know how much it leaks. 3.5 volumes per day at least. NASA gave us a lot more money, we would make it tighter. And when they go to the moon, they will as well. CO2 consumption, that's where your biomass is coming from. The carbon dioxide is making the long carbon chains of the green plant material, 0.22 kilos per day. And there's the electrical consumption in our system, about 100 kilowatts. 100 kilowatt hours per day. So that's 16-hour day. It's these kind of numbers. And while this sits up here a second, I'll say I have at least a number of students that are here. Erica is here. She knows how to operate the system, and she can grow a darn good crop in it. She's good at lettuce, as well as the others, and operating it remotely. But is Tyler? Tyler was here too. So they get some hands-on experience. So when they get out in the real world, they're not afraid to get their hands dirty and get involved with, get up front and personal with some of these plants, that's for sure. Here we are, 24 grams of biomass per kilowatt hour. This is total. This is edible plus non-edible, meaning everything, the roots, the stem, the leaves that we don't eat on the tomatoes. We count that as expensive biomass. That's where the carbon is going. When you reduce that down, you get rid of all the non-edible, then that's when you get the 13 grams of edible biomass per kilowatt hour. And we can do some calculations of that. The 13 grams is about 1/3 of an ounce. Well, keep that in mind. And if your kilowatt hour is 10 cents, how many 1/3 of an ounces do you need? 10? Right? What would that be? 3-ounce head of lettuce for $1 worth of electric power. Unless, of course, you're really good at getting that rate down.
How did you know about kilowatt hours?
I'm sure you did. I'm sure you did. This is a a number to throw out as a benchmark. But you should throw that out. I mean, that's what we need to know. That it seems to me that this number will help anyone make a decision about the efficiency of production, at least in terms of electric power. We did the same thing. You see labor, 36 minutes per day of labor use in the greenhouse. That is just as expensive to talk about. It's just as expensive for the astronauts as well. Probably the most expensive paid people in the world or out of this world are the astronauts. Although it's interesting that they, like the South Pole people, want to work with the planets. They've had opportunities. They've even eaten some of the experiments on the space station. So,
Gee, do you have payroll taxes?
Do I have payroll taxes? Well, the National Science Foundation, and thank you for your tax dollars, because that's what keeps that research station going now. So yeah, that's what you pay. Okay, that's part of it. And they get to have all the fun down there, freezing. Anyway, numbers. All right, and we just did some contrast. There's the 10 grams per kilowatt hour for the South Pole chamber versus 13 for the lunar greenhouse. I guess we got a little bit better than doing it. But in reality, we need to improve that almost by a factor of 10. And I think you can. I don't know when, but we're going to try. Certainly, we begin to get crops that would be more, more uniform, more of a monocrop. We have the possibility, should we get a phase 3, this has nothing to do with the story, but to have 3 more of these units together. And in doing so, we could put some monocrops and monitor them. We will see. But the lighting system, the nutrient delivery, telepresence, well, be able to know what's going on in your greenhouse without having to be there. We don't want to go to the moon as individuals. We don't want to go to Mars. Probably won't be coming back if you did. Or go to the asteroid, which is the next one we're talking about. You want to be able to know what's going on by sitting in your office and having it on a computer or having some control. But you want multi-crops. You can't just eat lettuce. I had a rabbit once and I fed it too much lettuce, and you know what happens. So we need other crops. And by the way, only half of the calories is not a bad approach to take, because these are minerals, vitamins, fiber, and very little calories. You need a lot of lettuce to get 1,000 calories in a 2,000 calorie diet. So you're going to have to bring the proteinaceous ground materials that can be stored for years, grains and all, as preparations for other food products. So we do the comparison. This is all, but if you ask me specific questions about how they were grown, what was grown, and Erica knows cowpea, black-eyed pea, strawberry, sweet potato, tomato, lettuce. I don't think we ever got a good cucumber in there, truthful. But there's some variety at least, and it's been very little done other than monocropping in these kind of test systems over the past 30 years. Here's Tyler. He's never late to work, but he will come in late to my presentation. And he really wants to graduate next year. Can you believe that? Thanks for coming, Tyler. You were introduced already, but he's the man who also knows how to grow. Anyway, these are questions that you have to ask, not only by the systems that are there, but how to put them together to have the crops that you need to grow, to fill up the areas as quickly as possible and get harvest out. Things you have to think about. Whether you're going to the moon, whether you're going to the South Pole, or whether you're in your backyard or in a commercial system here on Earth. I say that directly this information is of value for people growing in systems on Earth. Some of the temperature is 20 degrees Celsius, about 70 degrees Fahrenheit that we kept it at. We elevated the CO2 to 1,000 parts per million, and I think we can safely say we're up to about 400 parts per million naturally here on the Earth. Right now, when I started, it was about 320 parts per million, as I recall from science in 6th grade, which was a few decades back. I'll give you that for sure. Hydroponic systems, you see pH. 6.5, you see concentrations of the electrical conductivity relatively low, 1.8, something under 2 units, I'll just say that, of electrical conductivity is low. People go much higher and whatever. But there we go. We grew many crops in this, and here's a cross-section of the plants roughly at transplant, and emphasizing that you have to provide the energy source close to the plants and distribute that as uniformly as possible. We were just in the last session talking about the positive pressure greenhouse, how it can distribute the air temperature more uniformly than the negative pressure. Well, you have to have your lights to be able to distribute that light to all plants as uniformly as possible. And that becomes a challenge with LEDs. You guys are going to figure it out. I have not figured that out yet. Hydroponics, recirculating nutrient system. This is never do hydroponics this way. This is a vertical hydroponics. If you can envision nutrient film technique where it's a flat bottom, maybe 6 or 8 inches wide in a long row, well, this just take that horizontal and turn it vertical, is what we did, because it needed to be lightweight, out of plastic, collapsible. We have no framework at all. It's supported on a cable. Now you know why I asked that question if you're in that session about the cable. We span 18 feet, and we have a 3/16-inch diameter cable, aircraft cable, to hold these up, particularly with the tomatoes. Anyway, if you can imagine your clothesline, and then you just form a plastic sheet around it with Velcro to hold it together, what a great idea. It's not patented, but don't waste your time. No one will ever grow in this system, unless maybe they go off the planet. Controls and monitoring. This is a remote monitoring system and information that you could, at any time, just as we could, go and see on our website and see how the system is doing. And all the data is there. You're welcome to have all of it and do some analysis and give us some answers. It probably won't make much sense to you. We're still trying to figure it out. But information about liters per day of water production, amount of labor going on. We actually had the entire unit on load cells, so we could tell when lightweight Erica went in compared to heavyweight Brendan when he went in. Using cameras, not just to know what the plant looks like visually to us, but to do some of the spectral analysis, as you see in the upper right-hand corner, to get an impression of how healthy the plant is. We heard about, Caleb was talking about this. Yes, it's a very viable way. There's some PhD studies on that, and there's a long way to go with that to improve. Okay, thank you. You notice I have to thank a lot of people, because I really don't do any work. I just talk about it for the most part. Shift gears. I have a couple more minutes, and then we'll get to questions, or depends on the moderator, sir. Controlled environment systems to help feed the world, or at least provide them nutrition and minerals and fiber that we need to survive, and effectively use energy, water, labor, and capital. See, I had that in there. That was from a long time ago. It costs money to do this, and we should use it effectively. But controlled environments can be much more than producing food for feed. They can be basically space colonization, life support. They can be part of urban agriculture, as we're here talking about. It can remediate the air and the water. Plants take up salt water, which is the fertilizer, and transpire that water through the leaves into the air around the plants. And if we condense that water out of the air to reduce humidity, that's potable drinking water. So basically, salt water becomes fresh water, or heavy metal-laden water becomes fresh water, and the plant ends up with heavy metal, and then you discard the plant. Obviously not eating that. The last one I'll go right to, phytochemicals and pharmaceuticals, using plants to produce chemicals naturally or artificially to create, for example, we did have a tomato that could produce the hepatitis C vaccine. It was a GMO, obviously, special tomato, but it could produce that vaccine by a plant instead of doing it by the animal approach. That's possible. 5 great challenges leave you with something. You are good people. You're here for a reason. You also have challenges. And there's no silver bullet. There's a lot of things you have to learn and put together. So this is coming from an academic who's never had a real job outside of the university. I'm proud to say. So keep that in mind. That's where this is coming from. Know your market value, and know your competition, right? How long before they might catch up to you, or can you keep running faster than them? That is, grow it, but be able to sell it. Essentially. Education and experience. Climb that learning curve as fast as you can. Start small. Whereas, who was I talking to today? Don't start with 10,000 square feet. Start with 1,000 square feet or 500. Get your feet wet, no pun intended. Practice with hydroponics first on a small scale, then scale up. Of course, there's one way to scale up, to get up that learning curve. This is not your short courses, so there's a little added. Compliance with the situation. Know your local code officer. Work with the woman that was in the session this morning. It was great. Don't deal with the staff if they're giving you a hard time. Come talk to the elected official so you can get over the humps and the bumps. In our case, it wasn't an elected official. It was the engineers at Raytheon who we had to work with to get some of these things through to get to the South Pole. And there's my number 4. Estimate what your costs really are. Not just grams per kilowatt hour metrics, but other things. Grams per hour of labor. Grams per unit of nutrients used. All your expense sides. How much does it cost on a unit basis? All these things can be beneficial, obviously, to know. And to help, I would think, get the financing that you need along the way. To convince people that, yes, you can grow a crop, but you know what the costs are. Number 5, allow biology and physics to be your friend and work for you. Do not try to break the laws of biology or the laws of physics. It happens. It's attempted. It's always a failure, guaranteed. Educational programs, amazing, huh? Okay. This is actually a class of students, some of which are sitting here and have survived it. Where part of their laboratory is to grow a tomato crop in the greenhouse and be graded on it. And that's Dr. Rohrbach. She's just an angel in the way she can deal with the students, from psychology majors to artists to plant scientists to even unbelievable engineers. So, even engineers can't kill these tomatoes because, well, you do some things to help them out. The hydroponics system always has the water running. The computer keeps the temperature in control. But they have to take care of the nutrition and the insects and the pruning. And they get to realize that that seed planted or that transplant that they get in the end of August, the first day of class, that begins harvesting just before middle of November, is their baby. And they're responsible for it. And that's how you find the good students who want to go on in this industry. And those who would rather be something else. They can. Finally, the realities of growing plants indoors. I think I've talked to probably a number of people about this. This is something I thought was important to offer. We do a lot of short courses. This is a brand new one for us, but it's so closely related to what we do that I have several of my colleagues that are going to participate without a lot of concerns, because we're going to speak about the needs of the plant in a generic way, and the systems that you can put, the technical systems that can provide the needs, the environmental needs, whether that's in the root zone or in the aerial part of the plant in this system. And we're doing this in July. The beauty is that you come to Tucson, it'll be cooler for you people from Las Vegas, but for the rest of you, it'll be so hot you'll want to be inside and only grow inside and not even step into a greenhouse. But we'll look at real systems. We'll have some certainly technical presentations, applied technical presentations, information that you need to use. And then there'll be a grower industry investor networking opportunity that we're working on right now. You see some of the topics here. We'd really love to have you come to Tucson this summer in July. I think that might be it. So having said that, there is some time, 15 minutes. I would love to have questions if there are any. If not, then we have the video that I'd like to show. Do I run this, or do you want me to? You want to do it? Yeah, it's late. You know, that's the other downside of being last. We're all tired. I'm beaten, I'll tell you. And I don't think there's any liquor out there. There's no booze.
It's on the strip.
It's on. Oh, okay. All right. It's strip. Oh, okay. All right. Can I have your credit card number, please? Oh, yes, ma'am.
Can you tell us a little bit about the nutrients that you were using in some of these experiments?
Okay, in all of the experiments, we use inorganic fertilizers, out of the bag recipes that are well known and tried and true for these systems. We had to keep it as simple as possible. In reality, let me say, we tried to have a little chemistry lab down there and a scale, and you mix on your own, so that we knew there would be deficiencies we can add if we needed to and take away. We went to a 2-part nutrient solution in a matter of months because it was too difficult, too much work. I shouldn't say too difficult. They're scientists down there. They know how to deal with this. But they didn't want to. That's my guess. So we even went to a 1-part nutrient solution, which really is detrimental to tomatoes. It's hard to get all the nutrients that it needs. But we'll stay with an A and B solution, if you understand what that means. There's 2 different tanks, plus a tank of acid or a tank of base to change the pH automatically in the system. It's not to say we don't like organics and we haven't worked with organics. We have. It's still a challenge, and I'm not ready to really make any recommendations on that. Did that help? Yeah. Answer your question. Yes, back, standing up.
Yeah, I was wondering, kind of a 2-part question. One, do you have any industry partners that you work with, being like any corporate partners? And 2, what's the future look like for this program 5 to 10 years? I mean, without a government space program that I've heard of that would put anybody or cultivate any kind of a community on the moon, how do you put
That's a great question. That's a great question. Yeah, and it's a high risk for us. Keep in mind that the primary answer, if you were the dean or my department head, I'd say, what we learned from here, we're going to use on Earth. In fact, what we got here came from the past 40 years of experience in hydroponics and controlled environments. It's just fit into a NASA look. Because they don't want a box anymore. They want something that unit is collapsible. Not automatically yet, but collapsible manually, and it could go on one spaceship. So, the Sadler Machine Company is a small business that's probably less viable than we are financially. He has his heart in it not to make money. But we've also teamed up with international space agencies, space companies. It was mentioned that I went to Italy. I worked with 2, one very large, one that built half of the International Space Station. And they wanted to get into growing plants. So here, an agricultural engineer walking into an aerospace company where they did not know how to grow a plant. Are you an important person then? It's amazing. You can say anything you want, but you have to make it work. And then the same with both of them. So that's continuing. We plan for a phase 3. And we have a good chance of getting that. After that, the goal is to move this out of the research lab. Our thought was to move to the South Pole. This is Phil's thought, I should say. Is to take this to the South Pole, because the South Pole's environment is close to a good day on the moon. And even if you bury it in the snow, it's equivalent to burying it in the soil, the regolith of the moon. It's about the same. So it's built strong enough to be buried 1 meter below the ice, the snow in the dry valleys in Antarctica. Test it there. So National Science Foundation will get money from them. Or, sir, if you would like to speak to me later, I'd be glad to talk to you. We could get your name on the front door of this next unit. Did that answer your question?
It did, thanks.
And we're going to keep going because we know we need to do this because I think you will benefit from some of this. I hope so. If not, tell me what I'm doing wrong. Marco.
Hey, Gene, you were talking about how many grams per kilowatt hour. This is also important if you're expanding or building your facility, because that is the same information that you can bring to your local utility to get grants. And that can be up to 10% easy. So that number, I just want to emphasize how important that is, because it helps you with financing your facility.
Do you have a number from Bushel Boy?
Yeah, what I...
You don't have to say.
It was, well, what I put out to the utility was 13.5. Sorry, 135.
135, okay.
131, is that correct? But that was at 67 kilos.
Okay. All right, now at 110 kilos, I got a number from, I won't say who it is, but you know who it is.
Yeah.
Between 400 and 500 grams per day,
Yeah.
per square meter.
Right.
That's in a greenhouse using great solar radiation on a really good day. So half a kilo per square meter of tomato production.
We got a long way.
We're at 10 grams, right? They're at 550 times. So we have a ways to go, but they are in super optimal condition. The point is, they're just points on the wall that you need to aim for. See what you're doing. See where you fit. Then look and evaluate your situation to know where you should improve. Where's the most cost-effective thing you should do to your system to improve that number? I'm not telling you business people something wrong, but it just seems logical to me. Yes, Mr. Fu.
I just wanted to ask a question because I'm curious. Since especially for the Luna system, you're growing. I mean, all of them. You're growing the polyculture,
Yes,
and
polyculture.
for especially Luna system, you have space and resources at very limited capacity.
Yes.
So, why did you choose to go with the HPS that is central? Basically lighting. Because especially, and that's second question is, do you think you can optimize the yield by going more with the distributed LEDs and changing the photo periods for each crop?
Yeah, real tough questions. The first one's easy though. Why do we go to HPS? Because in the year 2000, LEDs were not on the top of my list, and probably not on a lot of other lists either. HPS was the way to go. You got to realize this is over 12-year-old technology. 14 years, sorry. Okay. Yeah, so the technology there was HPS. I'll still venture, and you can tell me the numbers, but we can still get more. We still get something on the order of 1.6 or 1.7 micromoles of light. That's the unit of light that the plants need per watt of input to that lamp. And LEDs are just exceeding that just recently, up to 2.1 micromoles per watt. If the Philips people are still here, they might argue that or explain why. But when I was told that by the Philips person, I said, I don't want 2.1, I want 21 micromoles per watt, and we're not ready to do that. Marco, you got an answer?
The modern HPS is also a 2.
There's HPS, you can get it 2 now? Okay. Ours are measured lower. Remember, we have that water jacket around it. That we lose 10% of our light because of that water jacket. But it saves us in cooling costs. Now, your discussion about how LEDs could be intermixed, that's part of phase 3. And we could definitely team up with you and your guys for sure, as a possibility in phase 3 to do that. But we will not learn in this little study how to optimize the use of LEDs. This is going to take a generation of research. You will be experimenting. Each one of you is going to be a little experiment. If Caleb was still here, he would maybe appreciate it if we could share your information about how you use lights, because it could direct the whole industry in a positive way. No pressure. But otherwise, you have to wait for researchers, or you're going to learn on your own, trial and error, wait for researchers that take a long time. We are really slow people. It's going to take a while. There'll be careers done on photobiology and lighting with LEDs because there's so many different things you can do, so many possibilities. Where when I started, you had a light bulb, you had a fluorescent tube, and if you had some money, you had an HPS lamp. That's it. Turn it on, turn it off. Now you can not only change the intensity, but you could change the quality of light, the color spectrum that you give that plant, and at different times of the day, and with different varieties, and different cultivars of varieties. Do we have a lot to do, or what? You must have a good question.
Just wondering if any of your work was inspired by Biosphere 2 and what's happening with that facility now?
Question about Biosphere 2. Well, all controlled environment systems inspire me. And I remember when I was in my younger years and heard about Biosphere, and in 1991, when the first group of 8 went inside and stayed there for 2 years to live off solar energy and recycle everything. That was an experiment of life support. What we do here is we don't allow students to live in there, and we don't recycle the waste. There's a whole thing I need to talk about where we're composting our biomass, and you know, we use all the water, 99% of the water that is, if we account for what's lost. 99% is used it goes in, it becomes part of the plant that is eaten, or it becomes unedible biomass, or it's recycled. Now once it's eaten, then the humans capture that water, so we have to reclaim that, so that will end up composting too. It's the first phase of cleaning up the salt water that we provide from our bodies. And then we'll feed it to the plant in the hydroponics system and let the plant have a next shot, polish that up, and then we drink the water coming out of the leaves of the plant, at least if we were the astronaut. So I like to say we're at least 2 steps away from the toilet before we drink the water. Do you have a sign in the bathroom, the women's room too? Do not drink the water in the toilet? Now tell me, when you walked in there, was that something that was on your mind? Yeah, I said, this is an interesting group when I'm there. Wow, they are hardcore recyclers.
It's especially interesting because most dogs can't breathe, and most cats deny that.
Okay, that could be that animal, the dog might drink that. Yeah, and somebody said when we were discussing it, because this was a discussion, it should be at the sink for us, right? Because we might drink out of the sink, but there's no sign there. Please cut that out of the video. I get in trouble all the time. But Biosphere was a great experiment, and it's still going on. It's now owned officially by the University of Arizona. That's operating for the $3 million a year budget, $1 million a year to run the electrical needs of that facility. But they're doing long-term ecological studies in there. No more fruit production. There's not an edible plant in there.